Hello and welcome. Today, we're diving into the hidden power behind pretty much everything that moves, pushes, and pulls in our universe. We're talking about force and pressure. Let's jump right in.
Just look at this incredible view from the SEA aquarium. That one single sheet of acrylic is holding back 45 million liters of water. And that water is pushing back with a mind-boggling force of 450 million newtons. To put that in perspective, that's like the weight of over 700 jumbo jets, all pushing against that one panel. I mean, how is that even possible? Well, to understand engineering marvels like this, we first have to get a handle on what a force really is. So here's our game plan for today. We'll start with the basics of force, then check out the difference between forces that have to touch and those that can act from a distance. Then we're going to clear up that super common confusion between mass and weight, see how gravity actually works, and we'll wrap it all up with a summary of exactly what you need to know. All right, let's get right to it. Our first section, what in the world is a force? You know, at its absolute core, a force is just a push or a pull. That's it. It happens when objects interact. If you think back to that aquarium, all that water is constantly pushing on the glass. That push is the force. It really is that simple and that powerful. And this is a great illustration of what forces actually do, right? A runner pushes against the blocks to start moving. Kids in a tug of war pull on a rope to try and stop the other team. You push or pull your luggage to get it going. So the key takeaway here is this. Forces change an object's motion. They're what makes things go, stop, or even just change direction. Okay, so not all forces are created equal. They basically fall into two main categories. And it all comes down to a really simple question. Do they have to touch or not? Let's explore contact versus non-contact forces. First up, we've got contact forces. And yeah, the name kind of gives it away. They only work when objects are physically touching each other. This includes things like the friction that grips a car's tires to the road, the air resistance that pushes against a cyclist, or even the table pushing up to support your coffee mug. We call that the normal force. And, of course, the tension pulling a wakeboarder along. In every single one of these, there has to be physical contact. And on the other side of the coin, we have non-contact forces. Now, these can feel a bit like magic because they act across totally empty space. The most famous one, of course, is gravity, the Earth pulling that diver down without a single thing touching him. But this group also includes the invisible push and pull of electricity and even magnetism. They all work from a distance. Okay, this next part is absolutely crucial. We're going to tackle one of the most common points of confusion in pretty much all of physics. What exactly is mass? Come on, we've all done this. You step on a bathroom scale, it reads 33.4 kilograms, and you say, I weigh 33.4 kilos. But here's the thing. From a physicist's point of view, that sentence is totally incorrect. Kilograms are a unit of mass, not weight. So what's the real difference? Okay, here's the official definition for you. Mass is the amount of stuff or matter in an object. Now, the most important thing to remember here is that an object's mass is constant. It doesn't change no matter where you are in the universe. You have the exact same mass on Earth as you would on the moon. We call it a scalar quantity, which just means it's a number, like 50 kilograms. There's no direction involved. So if mass is the stuff, then what's that number the bathroom scale is actually telling you? Well, that brings us to the pull of gravity and the real definition of weight. Right, so weight, unlike mass, is a force. It's the specific gravitational force that's pulling on an object. And because it's a force, its unit is the newton, not the kilogram. Plus, since it's a pull in a very specific direction, downwards, towards the center of the Earth, it's what we call a vector quantity. It has both a size, like 500 newtons, and a direction. So why does this weight force even exist? It's because any object with mass, like our planet Earth, creates something called a gravitational field all around it. You can kind of think of this field like an invisible area of influence. So when another object with mass, like you or me, enters this region, it experiences a pull, a force of gravitational attraction. That pull is its weight. So here's a quick question for you. We all know the Earth is way, way bigger and has a lot more mass than the moon. So with that in mind, do you think the gravitational field strength of the Earth is the same as the moon's? Just take a second and think about that. That's a great question, and the answer is actually hidden inside a really simple but incredibly powerful formula that connects mass and weight together. Let's put them side by side and see how it works. And here it is. W equals mg. Your weight is equal to your mass multiplied by the gravitational field strength. This is the key equation that links these two ideas. That little letter g tells you how strong the gravitational pull is at a certain place. Right here on the surface of the Earth, g is about 10 newtons for every single kilogram of mass. And this picture just illustrates the difference perfectly. This elephant has a mass of 1,000 kilograms. That's the amount of stuff it's made of, and that number is exactly the same on Earth as it is on the Moon. But its weight, totally different. On Earth, where g is 10, its weight is a massive 10,000 newtons. But on the Moon, where the gravitational field strength g is only about 1.6, its weight is just 1,600 newtons. Same mass, completely different weight. Okay, let's lock in these key differences one more time. Mass is the amount of matter, weight is a gravitational force. Mass is a scalar, just a number. Weight is a vector, it has direction. Mass is measured in kilograms, weight is in newtons. And most importantly, mass is constant everywhere, while weight changes depending on gravity. Seriously, this table is perfect for your vision notes. And finally, let's pull everything we've talked about together into a quick syllabus summary. This is exactly what you need to remember when that exam comes around. So here is your checklist for this topic. You have to be able to distinguish between contact and non-contact forces. Be ready to define mass, define a gravitational field, and define gravitational field strength. And of course, you've got to know that formula, W equals mg, and be able to clearly explain every single one of the differences between mass and weight. If you can do all that, you have totally mastered this topic. Wow, we have covered a ton of ground today, from the incredible forces in an aquarium all the way to the physics of an elephant on the Moon. And that brings us to one last thought-provoking question. We now know that weight is a force. So if you drop an object and its weight is the main force acting on it, what happens to its motion? Think about that one, and we'll explore the answer next time. Thanks for joining me.